Hey everyone, and welcome. Today, we're going to peek under the hood of the software that runs our entire world. We're talking about reverse engineering, which is basically the art of figuring out how a machine works when you don't have the instruction manual.
Okay, so picture this. You get this incredible new gadget, right? But it's a total black box. There's no instruction manual, no blueprints, nothing. So how in the world do you figure out what makes it tick? Well, that's the exact problem that reverse engineering tackles, but in the digital world. So let's talk about the work of a digital detective. I love this analogy. You can think of a reverse engineer as a kind of detective, or maybe even a digital archaeologist. But instead of digging through dirt for old bones, they're sifting through lines of compiled code. Their whole job is to piece together the original blueprint when all they have is the final finished product. Pretty cool, right?
So, to put it simply, reverse engineering is all about taking things apart just for the sake of understanding them. You see, when a company makes software, they usually keep the blueprints, what we call the source code, a closely guarded secret. So, what we have to do is work backwards from the thing they actually give us, that final program, to figure out all the logic and how it was put together in the first place. Okay, but to really get into this, to truly understand how a program works, we've got to go deep, like really deep. We need to learn to speak the native language of the computer's brain itself, the CPU. So at the very heart of your computer, you've got the CPU, the central processing unit. Literally every single thing your computer does, from opening a file to playing a game, it's all just the CPU running through a giant list of super simple commands, one after another. And what language does it speak? Machine code. Now, we're not talking about something friendly like Python or C++. No, this is the raw, gritty, fundamental language of the hardware. It's literally just a stream of ones and zeros. To us, it's complete gibberish. So, how do we deal with this gibberish? Well, that's where assembly language comes in. Think of it as our digital Rosetta Stone. It takes those raw machine instructions and gives them simple, human-readable labels. We call them mnemonics. So instead of a bunch of ones and zeros, you see something like MOV, which means move this data, or ADD for, you guessed it, add these numbers. Suddenly, we have a window into what the CPU is actually thinking. It's a total game changer. All right, but here's a little twist. Just like we have different languages and dialects all around the world, not all CPUs speak the same exact language. Their internal design, what we call their architecture, changes the rules and dictates the specific set of commands they can understand. The two big players on the field right now are x86. That's what powers most of your desktops and laptops, and ARM, which you'll find in pretty much every smartphone and tablet. And here's the key part. Each one has its own unique instruction set architecture, or ISA for short. You can think of the ISA as its own personal grammar book or dictionary for assembly. The rules are just different. And trust me, the differences can be, well, pretty huge. Just look at this. With Intel syntax, which you see a lot with x86, you say, move into this box, this number. The destination comes first. But with AT&T syntax, common in the ARM world, it's flipped. You say, move this number into this box. The source comes first. And it's not just the order. They use totally different symbols for everything. It's almost like learning Spanish and Portuguese. They're related, but you can't just swap them and expect things to work. Let's make this real. Here's the classic Hello World program on a standard x64 chip. You can see that first line, move, is basically telling the CPU, hey, here's the location of the text we want to print. That next line, XOR, that's a clever little trick to clear out a spot for some data. And then the grand finale, call_printf. That's the instruction that actually says, okay, go run the function that puts this text on the screen. Simple enough, right? Now, hold on. Let's look at the same thing but for an ARM chip. Whoa. Totally different, isn't it? Here's why. ARM was designed differently. The instructions are simpler and they're all the same size. Because of that, it actually takes two steps here, the ADRP and the add, just to do what x64 did in one. Point to the hello text. And then instead of call, it uses BL, which stands for branch with link, to jump to the function that prints the text. See, we're getting to the exact same place, but the roadmap is completely different. Okay, so how on earth does anyone actually do this? You can't just stare at a file full of ones and zeros and, I don't know, hope it makes sense? No way. You need a specialized toolkit. A digital detective needs their gear, right? And that includes both software and sometimes actual hardware tools. All right, on the software side of things, your number one tool is a disassembler. This is the magic wand that turns that raw machine code into the readable assembly we were just looking at. Then you've got decompilers. These are even more ambitious. They try to go one step further and guess what the original code might have looked like. And if you're working with a physical gadget, you'll need hardware tools, like a multimeter to check electrical signals, or even a soldering iron to tap directly into the chips.
And check this out. This shows you just how powerful these software tools can be. What you're looking at is a graph view from a really popular tool called IDA Pro. Instead of just showing you lines of text, it draws a map, a flowchart of the program's logic. So when the program has to make a choice, you see a split. You can literally follow the green arrow if the answer is yes, and the red arrow if the answer is no. It turns a confusing mess of code into a story you can actually follow.
And believe me, modern programs are not simple. They are these huge, complex spider webs of connections. This mind map here shows the structure of a typical Windows program file. You can see how it pulls in code from all these other shared libraries, where it stores its data, where its own code lives. It's all interconnected. A huge part of a reverse engineer's job is to map out and understand this entire web. So, okay, this is all cool and techy, but why does any of this actually matter? What's the point? Well, the applications are absolutely critical. Think about malware analysis. The only way to stop a new computer virus is to take it apart and figure out how it works. Cybersecurity experts do this to find vulnerabilities in software before the bad guys do. It's even used for things like making new programs work on old systems or for recovering precious data from a corrupted file. It's a really powerful skill. Okay, that was a ton of information, I know. So let's have a little fun and see what's stuck. I've got a quick 2-question quiz for you. You ready? First question up. What's the name of that human-readable version of machine code? You know, the one that uses those helpful little command words.
Got it? The answer is assembly language. That's our bridge into the mind of the machine.
All right, question number 2. Think back to that cool flowchart graph we looked at. What do those different colored arrows, like the red and green ones, coming off a decision point actually mean? And the answer is, they show the different paths the program can take. So a green arrow usually means the condition was true, go this way, and a red arrow means the condition was false, go that way. It's a visual map of the program's brain making a choice. Simple as that. And that really brings us to the final big idea for today. Think about it. Every single app on your phone, every piece of software on your computer, it's a black box, just like that gadget we talked about at the beginning. It's filled with hidden logic and secret pathways. So it really makes you think, what secrets are hiding inside the software you use every single day? Hey, if you had fun peeling back these digital layers with us today, then definitely hit that subscribe button, because we've got a lot more explainers coming your way. Thanks so much for joining me.